Ban itu वो लाइक वो हमको ये करना पड़ता है अंदर जो ठीक है कल का ठीक है ना अभी हम जो ये तो हम आते हैं ठीक है
Okay, good morning, everyone. Am I audible? Okay. Maybe just wait, huh? Okay. So last class we have discussed about the activated sludge process and also the design considerations that are involved in your activated sludge plant. Okay. So today we will just discuss something about the advantages and disadvantages of an activated sludge plant. Okay. Um, so there are certain okay. Am I audible or not? Okay, so roll number 120. Okay, You cannot hear because you have network issue. Okay, fine, no problem. Okay, later you see the video. I will upload it in the ERP, later you see. Okay, so there are certain advantages and disadvantages of your activated sludge plant over your trickling filter plant. So, what are those advantages and advantages of activated sludge plant? Those are like it requires your lesser land area. Okay, land area required is very less. Then the head loss in the plant is also very less. It is also quite low, and also there is no fly or odor nuisance. So there is no odor in your activated sludge plant, or there is no fly nuisance also. And it's also the capital cost of the activated sludge plant is also less. Okay, and there is also a greater flexibility of operation. Okay, the permitting control on the quality effluent is possible. So there is a flexibility also in its operation, and their control on the quality of the effluent is also possible. So what are the disadvantages of the activated sludge plant? It is that it has a high cost of operation. So here the cost of operation is very high, with greater power consumption. Then your machinery, a lot of machinery is needed to be handled, and also the sudden change in the quantity and character of sewage may produce adverse effects on the working of the process, thus producing inferior effluent. So somebody's mic is on, I think. Roll number 119, please mute your mic. I am hearing echo. Okay. So, your the sudden change, okay, like in the activated sludge plant, what happens? You have seen the process, okay. So there is a sudden change in the quantity and the character of the sewage. What happens? It may give some adverse effects on the working of the process, okay. So, thus producing what inferior effluent, okay. So the effluent will not be good if it produces some adverse effects. Okay, so like this, there are different, many advantages and disadvantages are there, and there are that if in respect with respect to the trickling filter plant also there is certain advantages and disadvantages also. So I would like to show you one video in YouTube, so you see that video and you will understand what does the what are the advantages in comparison of the trickling filter plant has with activated sludge plant. So you see this video.
Trickling filters, also known as biofilters, are normally a fixed-bed biological reactor operating in aerobic conditions. In the filter, microorganisms are attached to the inter-packaging material, which was composed of rocks or gravel in the past and is nowadays a wide range of plastic fill media. Fill media support is placed on the tank bottom, with wide openings that allow a good air and water mixing. Microorganisms on the fill media surface work on the removal of soluble organic matter from the settled sewage that is sprayed over the bed surface through a rotary distributor and is treated as it trickles through the fixed bed, navigating through layers of microorganism. The layers remove pollutants by both absorption and absorption-removing species like nitrite, nitrate, and others. Removal rates can reach up to 95%. In order to avoid clogging, a primary sedimentation process precedes the trickling filter. Also, the design of the rotary distributor has a high impact on the risk of clogging. The rotation velocity of the rotary distributor can be changed by either adjusting the incoming water flow or by using an electrical motor. As smaller the rotation velocity, as higher the water volume per square foot, and as bigger is the flushing effect. In time, the biofilm thickens and detaches into the liquid flow, forming the secondary sludge. Trickling filters are normally followed by clarifier or sedimentation tanks. The sludge collected is treated for reuse or prior to disposal. Among the main advantages of this system, it is important to highlight the resistant to shock loadings, high efficiency for ammonia oxidization, small land area required, final effluent is effectively stabilized. The system is self-cleaning, operating with low maintenance requirements. Operational costs are low since wear and tear are reduced due to limited use of mechanical equipment. Furthermore, in comparison with similar methods such as activated sludge, trickling filters are significantly more cost-effective as they don't require artificial aeration and have a smaller demand for operational space, resulting in cost reduction. Thanks for watching, and if you like our 3-minute tutorials, please subscribe and don't forget to give a thumbs up.
Okay, so you have seen the video. Okay, so those are, it was explained nicely in the video, the advantages of your trickling filter plant in respect to your activated sludge plant. Okay, so with this, we have like almost completed your treatment process chapter, but we have left some numericals. Okay, before I have left two numericals regarding your trickling filter plan, so there are certain numericals with that. So today we will do that quickly. We will do that two numericals. Okay. Okay. So, before going to the design problem of your trickling filter, we have to know certain considerations of your design problems. We should know some values. Okay. So, like while designing a trickling filter, you first have to design the the diameter and depth. Okay, so the diameter, it involves the design of the diameter of the tank, and it's also its depth. And also you have to design the rotary distributor that you have seen in the video. I have shown you one video regarding the trickling filter, so you have seen the rotary distributors, so you have to design that also, and the under drainage system also. Okay, so first there that you have to design the filter size. Okay, so you have to design the filter size, and that is based upon what certain loadings. Okay, so it is based upon the values of the filter loadings, and the filter loadings, it can be expressed in two ways. Okay, number one is your hydraulic loading and the other one is your organic loading. Okay, so what is what is a hydraulic loading rate? By, if you the quantity of sewage, okay, if it is applied per unit surface area, okay, per unit of the surface area of the filter, so per day, so that is your hydraulic loading rate. Okay, how much of sewage you are applying per unit surface area of the filter per day, so that is your hydraulic loading rate. And the hydraulic loading rate, it can be expressed in million liters per hectare per day. Okay, it is expressed in million liters per hectare per day. Okay, so there are two values of your like conventional trickling filter, and one is, we have studied, one is your high rate trickling filter. So both conventional trickling filter and high rate trickling filter will have two different values for your hydraulic loading. So the hydraulic loading for the conventional trickling filter ranges between what, 22 to 44 million liters per hectare per day. Okay, and for your high rate trickling filter, the value of hydraulic loading is what, 110 to 330. Okay, it ranges between 110 to 330, and normally between your 22 to 24, normally if nothing is given, then you can assume it to be 28 million liters. Okay, and between your 110 to 330 million liters per hectare per day, you can assume 220 value. Okay, now coming to the organic loading rate. So what is an organic loading rate? It is like the mass of BOD per unit volume of the filtering media per day. Okay, it is the volume, it is the mass of the BOD per unit volume of the filtering media entering per day. Okay, so this is your organic loading rate, and this organic loading rate is expressed in kg of BOD5 per hectare per meter of the filter per hectare meter of the filter media per day. So that certainly like your similarly like your hydraulic loading rate, so here also for your conventional trickling filters and for your high rate trickling filters, two values of organic loading rate is also present. So the conventional filter organic loading rate is what, it may vary between 900 to 2200 kg. Okay, and like for your high rate trickling filters, the value of your organic loading rate, it can ranges between 6000 to 18,000 kg of BOD5 per hectare meter in your high rate trickling filters. Okay, so now like why we find out the organic loading rate and the hydraulic loading rate. Okay, so the organic loading rate, for organic loading rate, we can find out the volume of the filter. Okay, by why do we need to find out the organic loading? So the organic loading value, it can give you the volume of the filter, and the hydraulic loading, it on the other hand, it gives you the area. Okay, it gives you the area of the filter. So like when you design a numerical problem, or when you design a trickling filter, you need to obviously you need to find out the area and the volume of the filtering media. So for that you will need your organic loading and hydraulic loading rate. Okay, so coming to next, now we will now we will be able to solve your numerical. Okay, but before that, also one more thing is there. Okay, so coming to the rotary distributor part. Okay, so the rotary distributor, it is also here mentioned that the filter diameter and the depth of the filter media, it is designed for average value of sewage flow. Okay, so the rotary distributor and the under drainage system and other connected pipelines, those are designed for peak flow, and it is again checked for the average flow. okay, but the filter dia and the depth is designed for what? Average value of sewage flow. One is for average flow and the other one is for your peak flow. But when you find the peak flow, again we have to check the check for the average flow. Okay, now coming to the efficiencies of the trickling filter. So there is one like certain formula. You see this formula, it gives you the efficiency of the filter, and it's like secondary clarifier in terms of what percentage of applied BOD removed. Okay, so this is your formula. You have to remember this formula for finding out the efficiency if it is asked in the like in the design numerical. Okay, then only you will have to use this efficiency formula, which is your 100 divided by 1 plus 0.0044 root over u. Eta is your efficiency, and what is u? U is your organic loading in kg per hectare meter per day. Okay, so now we will proceed to solve your trickling filter numerical. So the question has two part. Okay, this question has two part and it's a bit long numerical. So this question says that first part says that design suitable dimensions of a circular trickling filter. So it is said it is a circular trickling filter. Okay, circular trickling filter units for treating 5 million liters of sewage per day. So here how much of sewage is used per day? It is your 5 million liters of sewage per day, and the BOD is also given as your 150 milligram per liter. Okay, so the next part of the question, it says to design your rotary distribution system as well as your under drainage system. So first of all, we will do the first part of your numerical problem. Okay, so here since your your total BOD we need to find out, and for finding on the total BOD we have to multiply how much of sewage is coming per day and what is the BOD of the sewage of that sewage. Okay, so two values are given like 5 million liters and one is your 150 milligram per liter. So if you multiply both, and you will get the value of your total BOD present in sewage to be treated per day. Okay, so after finding so it is in milligram, so they are converting it to kg. Okay, so they are, it is in milligram, but they are converting it to kg, and so you got 750 kilogram. So 750 kilogram is the total BOD that is present in the sewage. Okay, so now you have to assume the organic loading. So as we have studied, so it is between your 900 to 200 kg per hectare meter per day. Okay, the organic loading value is between 900 to 2200, and so here in this numerical they are assuming 1500. Okay, they are assuming 1500, but it completely depends upon you whether you use 1500 or 1600 or 1700. It depends upon completely upon you. The numerical will not go wrong if you use 1600 or 1700 also. Okay, so they are using 1500 kg per hectare meter per day. So just now we discussed why we find out organic loading. Why organic loading we have to assume? Because we need to find out the volume of the filtering media. So now since you have assumed the organic loading value, so now you can easily find out the volume of the filtering media. So what is the formula? Like you have to divide the total BOD divided by your organic loading. Okay, total BOD divided by your organic loading, which is in hectare meter. So you have to convert this hectare into meter square. So finally, after converting to meter square or meter in terms of meter, so you get it 5000 meter cube. Okay, now you assume the effective depth of the filter. So this one also you can remember. You have to assume the effective depth of the filter as 2 meter. Here it is assuming 2 meter is the effective depth of the filter. Now you find out the surface area of the filter. Okay, so how you find out the surface area? You have to divide the volume of the filtering media divided by your effective depth. Okay, the volume is how much? It is your 5000 divided by your effective depth is 2 meter. So you got it to be 2500 meters square. Okay, now since it is mentioned in the question that it is a circular trickling filter, so you need a diameter of the trickling filter. So that diameter, since it is not given anywhere in the question, so you have to assume it. Okay, so here they are assuming a dia of 40 meter. they are assuming the diameter of 40 meters. So now after assuming the diameter of the circular tank, so they have to find out, or we need to find out the number of units required, how much of units of units are required, filter units are required. So how will you find out that? You will have to divide the total area you have found out divided by area of one unit. So total area you already got it to be 2500 meters square, but how will you find out the area of one unit? You have to, like, area of one of a circular unit will be pi by 4 d square, isn't it? So pi by 4 into what is d? D is a 40 meter we have just assumed now. So after solving you will get two numbers of units are required. Okay, so after finding the organic loading, after doing the organic loading, and after finding the volume and the number of units, now we will go to, like, we have to check the hydraulic loading. Okay, we will check the hydraulic loading. So how will you check the hydraulic loading? So hydraulic loading, we have studied that it is required to find out the area, surface area of the filter. So hydraulic loading is between your 22 to 44 million liter per hectare per day. So here in this question they took it to be 25 million liters per hectare per day. So how will you find out the surface area of the filter media? So it will be total sewage, okay, total sewage to be treated per day divided by your hydraulic loading per day. So which will be, total sewage is given to be 5 million liter in the question itself, and what is the hydraulic loading? They took it to be 25 million liters. Okay, so 5 divided by 25 hectares, they convert this hectare into in terms of meter, so it is 10,000 meters square. So you finally got the surface area to be 2,000 meters square. Okay, now you have got what you got the surface area is 2500 meters square, which is greater than 2000 square meter. That means for your filtering media to be like safe, you have to get the surface area to be greater than 2000 square meter. And here it is, after solving you got the surface area, it is greater than 2500 meters square. Okay, so it is safe. But you see, if you somehow, if you choose, you don't choose 25 million liters here. Okay, but if you get, suppose the surface area, it is less. Okay, if it is coming less, then what will you do? Again you have to redo your surface area part. Okay, you have to redo this part, and you have to choose some other value of hydraulic loading. Okay, but it should range between your this said values. Okay, like 22 to 44, if you have, it should be range between this, and you have to choose some other values of hydraulic loading, and then you have to see whether it is coming greater than 2000 square meter or not. Okay, so finally you got what? You got two units each of 40 meter diameter and 2 meter effective depth. So 2 meter is the effective depth, and if you add a freeboard, as I already told in each and every numerical, that you have to add a freeboard while designing a tank numerical. So if you add a freeboard of 0.6, so you will get the overall depth to be 2.6 meter, and this is your the first part answer. Okay, so now you have to design the rotary distributor. Okay, you have to design the rotary distributor. So how will you design the rotary distributor? We have already discussed in the design criteria that for the rotary distributors, they are designed for what? For the average flow, for the peak flow. Okay, so what is a peak flow? It is 2.25 times the average flow, and it is already, we have learned all these things in the very first day and second day of our class while we were doing raw water treatment. Okay, so it is 2.25 times the average flow, so peak flow. And what is the average flow? It is given here, it is your 5 million liters per day. So you have to multiply 2.25 into your 5 million liter per day. Okay, so you convert the million liter per day to cubic meter per second. So after converting, you will get, after converting the million liter per day to cubic meter per second, you will get 0.13 meter cube per second. Okay, so this flow, it should it have to be divided into two filter units. Okay, so you have to find the flow through each unit. Okay, so how will you find the flow through each unit? You just divide it 0.13 divided by 2. Okay, so you will get it to be 0.065 meter cube per second. Okay, now you have to assume the velocity at peak flow. Okay, like through the central column. You have seen the rotary distributor, so there is a central column there. Okay, you have to assume the velocity at peak flow. So the velocity, it is assumed to here it to be 2 meter per second. Okay, so now you have got the velocity, you can find out the diameter of the central column. Okay, so it is your the you know now q is equal to av, q is equal to av formula. So from there you find out the diameter. Okay, so you got the diameter to be 0.2 meter. Okay, so you provide a central column of 0.2 meter dia, but check the velocity through the column at average flow, as it should not be less than 1 meter per second or so. So while studying the design criteria, I have told that the central column, it flows for a average flow, but again you have to check it for, you have to check the velocity. Okay, you have to check the velocity for average flow. So now you have to check the flow velocity through the central column at average flow. Okay, so how will you check? So the discharge through each unit at average flow. So the discharge through each unit, so there is 2 unit, right? So through, if you find the discharge through each unit, that means the BOD that is mentioned in the question, it is 5, okay, divided by 2. So you will get 2.5 million liter per day. So now you convert this million liter per day to meter cube per second. So you will get 0.029 meter cube per second. Now you can easily find out the velocity at average flow. Okay, it is discharge divided by pi by 4 d square. What is d? It is 0.2. Just now we got of the central column. Okay, so it is your 0.92 meter per second. Now you can see that this 0.92, it is coming less than your 1 meter per second, but it is already mentioned that the velocity at average flow, it should not be less than 1 meter per second. Okay, but here you can see it is coming 0.92 meter per second. That means it is coming less than your required value. So what will you do now? So you will have to assume another value of your diameter. Okay, so we have chose 0.2 before. So now you have to, you slightly reduce it. So you can choose the value 0.19 suppose. Okay, so 0.19, using the dia as 0.19, now you find out the velocity again. Okay, so now you got it to be 1.023 meter per second, which is greater than 1 meter per second. So this diameter 0.19 meter is required, or it is permissible for your central column. Okay, so now this numerical is almost complete, but this next page, I didn't have the next page with me right now. So next class, I will be completing this numerical. Okay, some little part is there left there. So we will complete that, and I will share this PDF with you also. Okay, so it's only 5 minutes, 4 minutes left. So I have to quickly take your attendance. Okay. Roll number 51. Roll number 51. 52.
Present, ma'am.
52. 53. 54. 55. 56. 57. 58. 59. Who is there?
57.
57. Okay.
57.
57. Then 58. 59. 60. No one is there. Okay. 61.
मैम 61
Okay.
का नेटवर्क खराब है, वो प्रेजेंट है।
किसका?
61 आरिफ खान।
ओके 61 ठीक है 61 का दे दिया 62 63 64
Ma'am,
65
63.
okay 63 64 65 66
Yes, ma'am.
okay 67 68
Yes, ma'am.
67
Yes, ma'am.
okay 68 69 70
Present, ma'am.
70 right
Yes, ma'am.
okay
70.
71
Present.
okay 72 73
Present,
7
ma'am. 73.
okay 74
Present, ma'am. 74.
okay 75
Present, ma'am. 75.
okay 76 77
Present,
76
ma'am.
Ma'am.
okay 76 is there 77 is also there 78
Yes, ma'am.
okay 79
Yes, ma'am.
okay 80 81
Yes, ma'am.
82
81.
okay 82
82 present, ma'am.
okay 83 83 is there
Present, ma'am. Yes,
okay
ma'am.
okay 84
Present,
eight,
ma'am. 84.
okay 85
Yes, ma'am.
okay 86 87 88
Yes, ma'am.
eight,
88 present.
Ma'am,
okay
87.
okay
87, ma'am.
87 okay 87 88 89 90 91 92
Yes,
90,
ma'am.
92
Yes, ma'am.
okay 90 is there
Yes, ma'am.
okay 90 90 92 now 93 94
Yes, ma'am.
94 95
Yes, ma'am.
okay 96 97
Present, ma'am. 97.
okay 98 99
98 present, ma'am.
98 okay 99
Yes, ma'am.
okay 100 101
Present, ma'am.
okay 102
Present, ma'am.
okay 103
Present,
104
ma'am.
10
103.
okay 104 105 106 107